I'd like to start in Chapter 6, that's in series parallel circuit. Back in Chapter 4 and 5, we look at series and parallel circuit. In Chapter 6, is combination. You might have a circuit that has both series and parallel circuit or parallel series circuit. So let's take a look at that. And then we'll look at a set of problems in that chapter. So either you're going to have a series parallel circuit or parallel series circuit or combinations. For example, if I look at this circuit right here, R1 and R2 are connected in series, R3 and R4 are connected in series, and then the sum of R1 plus R2 is in parallel with a combination of R3 plus R4. So if I look at the terminal here, R total then would be equal to R1 plus R2 in parallel with R3 plus R4. If I look at a different circuit, now this is series parallel, circuit A. Circuit B is parallel series. So you got R1 and R2 connected in parallel, R3 and R4 are connected in parallel. Then R total would be equal to R1 in parallel with R2 plus R3 in parallel with R4. Let's look at a simple example. Let's say you have 36 volts connected across 10 ohms, 15 ohms, and then 10 and 2 ohms. And we want to look at how much current is drawn from the source, I total. We're also interested in R total and also the current I1 in this resistor here, 10 ohm resistor. So to calculate R total and I total, so you always do reduce the resistance to come out with R total. So the first thing you want to do is calculate R total. If you notice, 10 and 2 are connected in series. 10 and 15 is connected in parallel, so you do that. 10 plus 2 is 12. Then you have 10 in parallel with 15 and in parallel with 12 ohm resistors. You got 3 resistors in parallel. So you can combine them 2 at a time, or you could just simply do R total is equal to 1 over 10 plus 1 over 15 plus 1 over 12. But if you do 2 at a time, 10 in parallel with 15, that's product over the sum. 10 times 15 divided by 10 plus 15 is equal to 6. That's 150 divided by 25. Now you got 6. Replace this 2 by 6 ohm resistor. Now you have 6 in parallel with 12. And to do that, you got 6 times 12 divided by 6 plus 12, and that gives you 4 ohm resistor. So 36 volts then at this terminal is going to see only a 4 ohm resistor. So if I look at I total, then would be equal to 36 divided by 4, that's 9 ohms, 9 amps. So that gives you R total, I total. If you're interested in determining the current I1, if you notice, this point is the same as on one single node, and everything in the bottom is just a circuit is drawn differently. And bottom is also one single node. So 36 volts is directly across 10 ohm resistor. So the current I1 just simply 36 divided by the resistance 10 ohms. So that gives you 3.6 for the current I1. Now, every time you're dealing with the parallel circuits, you excuse me, interested in loading effects. There are 2 categories that we're going to look at loading effects. One is the voltage divided loading effect, and another one is a voltmeter loading effects, because every time you measure a voltage across a given load, you must put a voltmeter connected in parallel with it. And when you do that, it really does have a loading effect, unless the voltmeter is ideal. But every time you put an instrument to measure the voltage or currents into the circuit, you will create a loading effect, just like you did with a series circuits. When you measure the current, you introduce some kind of a loading effect due to the ammeters, because it's connected and inserted in series with the circuit. So let's look at a voltage divider. It's commonly used to provide a voltage at different levels, of course. If I look at a 12-volt source, and let's say you need 3 volts on the output, then you can always use a potentiometer, let's say 1 k ohm potentiometer, and you can set it up as terminal A, B, and C is the adjustable one. So you can determine what the pot setting is to determine to give you a 3 volts. So we're interested in whether that resistance R1 and R2 such that you have 3 volts in output. Well, you can do a voltage divider rule. If I'm interested in 3 volts here, so 3 volts has to be equal to the total voltage, 12 volts, times R2 divided by R1 plus R2. So we'll really have one equation with 2 unknowns, but we have R1 plus R2 is equal to 1 k ohm resistor. So from here you can determine, plug in R1 plus R2 with 1 k ohm resistor, which is 1,000 ohms. So you only get one equation, so you can determine what the resistance R2 is. That would be 1,000 times 3 is 3,000 divided by 12 is equal to R2. That's 250 ohms. And if R2 is 250, then R1 has to be 1,000 minus 250 is 750. So you can easily use the voltage divider rule to determine the pot setting to give you the output voltage, set an output voltage, in this case is 3 volts. Now that you have this 3 volt supply, every time you put a load across it, let's say R of L, and let's see what happens to that 3 volts. Ideally, you like to keep that 3 volts, the output at 3 volts. But we can see that when you put a load across it, you're definitely going to have a loading effect. And let's see what happens. We're going to look at 2 cases. Case A, if R of L is equal to 250 ohms, we want to calculate the voltage V sub 0. Well, when you do that, when you put a load across it, you're going to change the circuit. Now you have 250 in parallel with 250. So you need to find a parallel combination of those two. And then if you got 2 resistors identical, 250 and 250 in parallel gives you 125. So you really change the circuit from 250 ohms down to 125 if R of L is small or very close to your R2 setting of your pot. So if I calculate the output voltage now, the V sub 0 then would be 12 volts times 125 divided by 750 plus 125. It gives you 1.714 volts. And that's a significant drop in the voltage as soon as you put a load on it. So you really have a poor voltage regulation. So if I look at the calculated percent error, it would be V actual, which is 3 volts, minus V measured, divided by V actual. It goes from 3 volts to 1.714 divided by 3. So you have 42.57% error. So that's not too attractive. Let's look at a case if R of L is equal to 10 kilo ohms. So you put 10 kilo ohms in parallel with 250. Now if this resistor is very large compared to R2, then you have a very current going to go to that resistor, and most of the current, ideally when I total is coming in, all of it go to 250 and nothing to the load, or a very small portion of it, such that you keep the voltage where it is. So I of L then will be very small compared to I of total if this resistor is very large compared to the R2. Let's just calculate it to see what you come up with. 250 in parallel with 10K, it gives you 250 times 10,000, or 250 plus 10,000, and that gives you 243.9, which is as close to 250. So the combination of these two, it drops the resistance to 243.9. Now if I look at the output voltage, then it will be 12 times 243.9 divided by 243.9 plus 750. So you're doing voltage divider there. So the voltage will stay at about 2.945 volts. Now if you calculate the percent error, it's 3 minus 2.94 divided by 3 times 100%. That gives you about 1.84%, which is okay, anywhere between 2 to 3% drop in the voltage is acceptable in most applications. So therefore, R of L of the load has to be much greater than R of 2. The rule of thumb is at least 10 to 1 ratio in order to have a good voltage regulation or minimize the loading effect as soon as you put a load across your output. Second one is the voltmeter loading effect. And to do that, let's look at a simple example. Let's say you have two resistors connected in series, R1 and R2, and it's hooked up to a 6 volts source, and we want to calculate the measured output voltage is across that R2. Well, ideally, the calculated value would be equal to the expected value. You could do a voltage divider. V2 is equal to 6 volts times 20K divided by 10K plus 20K. If you calculate that, it gives you 4 volts. That's what you expect across R2. Now, if I use a voltmeter, let's say it's analog voltmeter, or you can use a digital voltmeter. So let's look at analog voltmeter. That's on a 10 volt scale because you're expecting 4 volts, so 10 volt scale would be good, with a sensitivity of 20 kilo ohms per volt. The sensitivity determines what is the internal resistance of the voltmeter on a different scale. So the voltmeter is on 10 volt range, and the sensitivity is 20 kilo ohms per volt. R1 is equal to 10K, R2 is equal to 20K, but then you put a voltmeter there, you're really putting a resistance R of M in parallel with it, just like we did with a case A with the voltage divider loading effect. Now, the R of the meter, if it's 20 kilo ohms per volt, so for every volt you have 20 kilo ohms. So the R of the meter is always equal to sensitivity times the range, or a scale. R of M is 20 kilo ohms per volt. You're on a 10 volt scale. Volt and volt cancel out. So internal resistance of the meter then would be 200 kilo ohms. Again, so as soon as you put a voltmeter across the load, you're really putting 200 kilo ohms resistance in parallel with your output R2. Now, if you want to measure the V2 measure, then it would be equal to 200K in parallel with 20K times 6 divided by 10K plus 20K in parallel with 200K. So every time you use a voltage divider rule, you must have only 2 resistors connected in series. So first you need to convert this to one single resistor, 20K in parallel with 200K. And if you do that, 20 times 200 divided by 20 plus 200, that gives you about 18.181K. So the V measured then would be 6 volt times combinations, which is 18.18, divided by 10 plus 18.1818. That gives you about 3.87 volts, and to calculate the percent error, it will be 4 minus actual minus measured divided by the actual value, and that's about 3.25% error. Now let's look at the case if you use a digital multimeter. So if you instead on a digital voltmeter, now most voltmeters have 10 to 11 mega ohms fixed internal resistance, and so they'll be more accurate. Then let's see what happened to the percent error. So again, you're going to repeat the same calculation, except the R of the meter is now 10 mega ohms. So it'd be 10 mega ohms with 20K in parallel. 20K, 10 mega is 10,000 kilo ohms. So make sure you have the same units. Divided by 10,000 K plus 20K. So it'd be 20 times 10,000 divided by 10,020, that gives you 19.96. So with a large internal resistance to the voltmeter, you can see it has very small effect on the resistance R2. Now if you use a voltage divider, now the V2 measure would be 6 volts times the combination, which is 19.96, divided by 10 plus the combinations. And that gives you 3.997 volts, which is very close, much closer than previous with the 200 kilo ohm resistors internally. And if you calculate a percent error, that's 0.0667%, so which is very insignificant. One of the applications of series parallel circuit is Wheatstone bridge. Wheatstone bridge has 4 resistors, R1, R2, R3, and R4 are connected in that configurations. And you have a very sensitive ammeters called Galvo. So the G is the Galvo abbreviation is a galvanometer. It's a very sensitive and inexpensive ammeter. Measures current is less than even 0.1 micron, so it's extremely sensitive. By adjusting R1, R2, and R3, and R4, it's possible if you can null the Galvo such that there's absolutely no current flowing to the meter here in the middle, inside our bridge. When that's the case, they say the bridge is balanced, and let's see what happens, at what conditions you will have a balanced bridge. Now, if V1 is equal to V2, then the voltage across the Galvo be V1 minus V2 divided by its resistance, so the current would be 0. So the V1 is equal to V2, Ig is equal to 0, and it acts like an open circuit. So that's what the circuit is going to look like if there's no current going to the Galvo. Now I can redraw that circuit. That's the voltage V1 and the voltage V2. And we're going to call this voltage from here to the from this point down here as the plus or minus V terminal. So if I redraw that circuit, you can see now there's no current is flowing to the Galvo. You can remove it. Now R1 and R2, they'd be connected in a series because you got to have the same current. Whatever the current is coming in here, it's not going to go to the Galvo anymore. It's going to the resistance R2. Therefore, R1 and R2 be connected in a series. So if I redraw that circuit, it's going to look like that. And the same thing within this side. On the right, you got R3 connected and R4 they connected in a series. And then you have R2 connected in a series will be in parallel with a combination of R3 and R4 connected in a series. Okay. So I can use a voltage divider rule. If I look at the voltage V1 is equal to the voltage from here to here, which is the V total, or V terminals, times R2 divided by R1 plus R2. The same thing in this side. The voltage V2 is still hooked up to the same voltage. They're in parallel. Will be V terminals times R3 divided by R3 plus R4. If V1 is equal to V2, then let those two equations to be identical. R2 divided by R1 plus R2 has to be equal to R3 divided by R3 plus R4. Cross multiply it, be R1 R3 plus R2 plus R3, R2 R3, and then R2 R4. R2 and R3 will cancel out from both sides of the equation. Then you're left with R1 times R3, R1, oh, I'm sorry, that should have been R3, yeah, R1 times sorry about that, that's a typo. It should be, this should be V2 would be equal to, use a voltage divider rule, V2 would be equal to R4 divided by R3 plus R4. So you multiply it out. Let's see, you got R1 be R4 times R1. So R3, that should be R1. Sorry about that, you can make that correction. So R1, it turns out that R1 times R4 has to be equal to R2 times R3. So that should be interchanged. So that should be R4 and this should be R3. Yeah. The opposite. So please make a note of that. That should be R1. R4 has to be equal to R2 times R3. So therefore the bridge is balanced and the current, there's no current going through the galvo. What they usually do with the Whinstone bridge to measure the one of the applications of the Whinstone bridges to measure the resistance extremely low, so it's a very sensitive ohm meter. That's one of the applications of it. What they really do, you adjust R1 and R2 are fixed. R1 and R2 are fixed, and then either R3 or R4 is a variable resistor, extremely sensitive variable resistors, and then you put your unknown resistor either in R4 or R3, it doesn't matter where you place it. So when you do that, then you can solve for the resistance R4 or R3. If it's R3 is unknown, then R2 or R1, those are fixed, so you know that becomes a multiplier. And then by adjusting R4 as a decade box or variable resistor, then you can determine what R3 unknown resistor is. So you can put R3, you can make that R of X. Sometimes you want to calculate it. One of the application would be is unbalanced conditions. When the bridge is unbalanced, the other application of the Whinstone bridge is here, if the bridge is balanced, you pick R1 times R4 to be the same as R2 times R3. If you do that, then the bridge is balanced. What you can do is you can put some kind of a photoresistor in one of the resistance here, let's say R2, and then like if you look in the revolver door or automatic door in the supermarket, as soon as you get closer to the elevator, then because the light intensity is changing in the resistor, the photoresistor, its resistance will change and the bridge will no longer be balanced. If the bridge is unbalanced, then the voltage of V1 and V2 will no longer be the same. And so you have a very small voltage drop, and then you have current flowing. And what they do is hook that up to operation on differential amplifier. Then you amplify the voltage here, and that will hook up to some kind of actuator to close or open the door. So if the bridge is unbalanced, we should be able to calculate how much current is going to develop to the galvo and how much voltage you're going to have at point 1 and 2. That becomes unbalanced bridge. So unbalanced bridge, R of G is there. We're going to call that the resistance of the galvo. Now if you look at the circuit, unfortunately no longer these are connected in parallel nor connected in series. R1 and R3 are connected in parallel at point A, but at point B there's another elements between point B and C, so they're not connected in parallel, nor the resistance R1, R2, or R1 and RG are connected in series. To get around this, to come up to see what is R total to calculate the I current, before I forget, if you've noticed here, the unknown resistor is not function of the voltage you're putting in. So if you galvanometer or the Whinstone bridge to measure the resistance is no longer a function of the internal battery. If the battery is even dead, you can still have very small current flow. So the unknown, the measurement is not really a function of how much voltage you have in your power, so in your battery. So it's independent of the source of the Whinstone bridge. To come up with R total, to simplify the circuit, there's a technique called delta to Y transformations. if I look at this delta connection, R1, R3, and R0 are connected in the form of a delta. If I convert that into the Y connections, so R1, R3, and RG, if I convert that to R of A, R of B, and R of C with a point A, B, and C again, then I should be able to combine the resistance to come out with R total. That's called Y delta Y or Y delta. You can do it either way. You can do delta Y and Y delta transformations. The people they're doing with a three-phase power, especially power transformers, they have the transformer either connected in delta or Y, depends on the applications. If you're jacking up the voltage, it's connected up as a delta Y. The primary of the transformer is connected to delta. The secondary of your transformer is connected to Y. And if you want to do a step down at the voltage, in order to reduce the transmission losses, the power company jack up voltage due to the delta to Y power transformers from up to about 765,000 volts to minimize the transmission losses over a long distance. And then when you get to the distribution center in an area, then they drop it down again. They do that by using Y delta power, three-phase power transformers. So the power companies or the power engineers that constantly do delta to Y transformations for the calculation purposes. To do that, let's say I'm looking at terminal A and B in delta, I'm going to call that R of A, B delta. I'll do the same thing in a Y connection, so I'm going to call that R of AB, the resistance at a terminal A and B, I'm going to call that Y. Now, if I do R of AB delta, then when nothing is hooked up to the point C, then R3 and R of G are connected in series in parallel with R1. So that's what the circuit is going to look like if I'm just going to look at a terminal A and B. Therefore, you got R1 in parallel with R3 plus R of G. And to be product over the sum, so it's going to give me this expression right here. So I'm going to multiply it out, be R1, R3 divided by the sum, plus R1, RG divided by the sum. I do the same thing with a Y connection. If I look at a terminal terminal A and B, R sub C is not in the circuit, then you simply see R of AB would be simply be equal to R of A plus R of B. So then R of A, B, and Y is to be R of A and then R of B. So if I like the delta to be the same as Y, then I'm going to force R of AB delta to be the same as R of AB Y. Then I'm going to let this be equal to R of B and let this to be equal to R of A. So that's delta, and then I can calculate A, B, and C. So R of A would be equal to the first one. It doesn't matter which one you do, it comes out to be the same. So if I let R of A to be equal to R1, R3 plus, divided by R1 plus R3 plus R of G, and then let R of B to be equal to R1, RG, second term, let that be equal to R of B. So you calculate R of A and R of B, and then you can repeat the same thing next time you're going to look at a terminal, let's say B and C from delta, and you look at B of C from Y. When you do that, you can go through the same calculation again, and you come up with R of C. If you notice, the denominator will be the same on all three of them, or we did R and R of B, and then the numerator will be the product, be R3, R1, R1 RG, so of course then R sub C then would be equal to R3 times R of G. So if I have R1, R3, and RG, and if I put, that's your delta, I'm going to put a Y right in the middle. You don't really need to memorize that equations, those two equations, or three equations. The way it turns out, if I want to calculate R of A, then would be equal to the product of the two resistors on both sides, would be R1, R3 divided by the sum of the three. And then if you want to calculate R of B, then it would be equal to R1 times RG divided by the sum of the three. And if you want to calculate R sub C, it's just simply R3 times RG divided by the sum of the three. Now that you did a delta to Y conversion, you can completely replace this part of the circuit, the delta part, between point A, B, and C with the Y connection. That is going to look like this. So R of S, that point A, this is your delta, now is converted to Y. Now if you notice, now R sub B and R2 are connected in series, R sub C and R4 are connected in series. And then those will be connected in parallel, so if you plot a circuit, it's going to look like that. These two connected in series, these two connected in series, that's series parallel circuit. And then the results of these are connected to R of S and R of A. So R total then would be equal to R of A plus, if I'm looking at R total here, R of S is a part of the source, so the total resistance here after the R of S from this point to this point would be R sub A plus R sub B plus R sub 2 in parallel with R sub C plus R of 4. And once you do that, then you can calculate what R total is, you can calculate what I total is, then you can determine what the current is or the voltage at every point. Point B and C is give you the voltage at the terminal voltage V1 and V2. That's pretty much what I want to cover in that chapter. We have a set of problems we're going to look at in chapter 6, problems 7, 10, 15, 19, 23, 25, 29, 37, and 41. Please make that corrections in that equation. That should have been, when you do a voltage divider here, since we measure this voltage from here with respect to the ground here, that was V1 is V total, or V terminal times R2 divided by R2 plus R1. And the same thing here. That should have been, or you can change that to R3, make that R4 would be okay. So just swap R3 and R4, then the equation would be okay. And then you get R1 times R4 has to be equal to R2 times R3. All right, we'll stop here, and next time we'll look at some of those problems in chapter 6.